Good morning, class. Today we're going to talk about experiment 17, which is the molar mass of a gas. And in this experiment, we're going to determine the molar mass of lab gas, which is methane, and an unknown gas. So, if we're going to determine the molar mass, we're going to need a sample, and we need to know the mass of the sample and the moles of gas in the sample. There's actually two ways to do the math. One way is better than the other. Let me explain both. So here's the definition of molar mass. I rearrange it to isolate moles. Moles is the mass of the sample divided by the molar mass. And now I'm going to substitute moles into our ideal gas law and do some rearranging. Now I rearranged it and I can solve for the molar mass. What I need is a sample. I need to know the temperature, the mass of that sample, the pressure, and the volume. So I need 4 measurements to determine the molar mass by the first way. So in lab today, we're going to be, I'm going to be collecting, Stu and I are going to be collecting a sample. And the volume of our sample is going to be 60.0 mils using a syringe that has a place where the stockroom has burned a hole in it, so we can put an iron nail in there that makes it stopper right at 60.0 mils. So that's the volume. The pressure is going to be whatever the barometric pressure is today, which we'll get off the barometer or from weather.com. The temperature is the ambient temperature in the room. And then the mass we're going to measure on a balance. I'll talk more about that in a minute because measuring the mass is a little bit tricky. Okay, that is one way to determine the molar mass. It works as long as you know the pressure, volume, mass, and temperature of a sample at a given moment. But that's 4 measurements, and every time we make a measurement, there is some error inherent in that measurement. A second way, a better way, would be to compare the gas we're trying to determine to a gas that we know. So we're going to use a reference gas, which is air, and at ambient conditions, that means what the conditions are now, 1 atmosphere of pressure, room temperature. We know the density, we know the molar mass of that gas. Okay, so I start the second derivation the same way. I'm using the ideal gas law. I rearrange to solve for M. I'm using my rearranged molar mass equation to substitute for M. And then I'm gonna, now I have an arrangement where on one side of my equation I have a measurement, which is mass, and the molar mass, which is what I'm solving for. And on the other side of the equation, I have P, V, and T, but if we make all these measurements at the same time, they should be the same value. So even without measuring them, and therefore having no error that is inherent in any measurement, I can treat them as a constant and say the mass over the molar mass of my reference gas is equal to the constant, PV over RT, which is equal to, as long as P, V, and T are the same, the mass over the molar mass of my unknown. So I rearrange to solve for the molar mass of the unknown, which is the goal of the lab. And now I just need 2 measurements, the mass of my unknown gas and the mass of the reference gas, which is air. And I take a known quantity, we know this to 4 sig figs, the molar mass of air at this temperature and pressure. So the beauty of the second way is we're only really making 2 measurements, and the measurements are mass. And what's good about that is the analytical balance gives us mass where you're estimating the 4th digit. So it's a pretty reliable number. So there's less error inherent, and we get more sig figs. Okay, so now I'd like to talk about how to measure the mass of a gas, because that is a little bit tricky, and I need to talk about buoyancy. So I weigh as much as I weigh, and I have a certain, mass that gravity is pulling to the ground. But when I get in a swimming pool, I feel like I weigh so much less. I'm so light. Is it true? Do I weigh less in a swimming pool? No. It's because the water has a buoyant effect on my body. And that happens anytime we have the thing that is measured, the weight of me, displacing some fluid that it's measured in the case of the pool, that's the water. But what we're doing today in a lab fluid is the air around it, there is that buoyant effect. So I need to talk about that for a minute. I have a spring scale here. It measures weight in newtons, and if I just take this cup and the mass in it, and I get the mass in newtons, not the mass in newtons, the weight in newtons, it's 1.55 newtons according to this scale. If, let's see, if I take this same system, so I have the mass inside the bucket that's holding it, and I stick it in water, the apparent weight is a lot less. And when I read the spring scale, it says that it only has a weight of 0.25 newtons. So there's 1.3 newtons that are apparently missing. Are they really missing? No. It's just there's a buoyant effect from water. How great is that buoyant effect? The buoyant effect is the same as the weight of the displaced fluid. So this bucket hasn't changed size. I'm filling it with water. I see what the weight is in newtons. And it turns out the weight in newtons is the same. The apparent buoyant effect is the same of the mass of the displaced fluid. When we're in water, the displaced fluid was water, I needed the weight of that. If we're measuring 60 milliliters in air, there's 60 milliliters of air that have been displaced, I need the weight of that. Why does that matter? Well, you might think, if I want to know the mass of the syringe, and then we're going to add a gas and get the mass of the syringe with the gas, the mass of gas is just the difference in those two, but it's not true. And we're going to prove that to ourselves by collecting some numbers. What I really need to do is get the mass of the syringe when it's open to the same volume. So Stu, I'm going to need you. When it's open to the same volume but contains nothing inside. So here's a nail. Okay.